Now we're on to the sequences and series question. So we have one, I'm just going to count the total bricks first, or the total blocks, 1, 9, and this one is 25. So it's 1 squared, 3 squared, 5 squared. So I'm pretty sure the next one's going to be 7 squared, so it's going to be 7 by 7. So if I do 7 blocks here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. So it's got to be 7 blocks total. And you'll have to excuse the width of one or two of them there. So now I'm going to get 49 blocks in total, and by the looks of it I have to shade in the main diagonals. So the main diagonals, go for re-grey here, 2, 3, 4, 5, like so. And there you go. So it's just a matter of counting the amount of greys and the amount of whites in each pattern, and we're all very much capable of counting. So I'll just nip through this really quickly. The number of grey squares in the second one was 5, and then the third one it was 9, and the one I just drew there was 13 grey squares, and then the number of white squares was 0, 4, and then 16 and 36, and then if we add them all together that's 1, 9, 25 and 49, which is what we're expecting. Okay, so cool, we just did that. Verify that the number of white squares in each pattern forms a quadratic sequence, and hence show that the number of white squares in the nth pattern of the sequence can be represented by this function here. Alright, no bother. So it's, what's it, 0, 4, 16, 36. 0, 4, 16 and 36. Is that correct for the white ones? Okay. Now let's see this. Let's verify it's a quadratic. Now, if it's a quadratic, the second differences will be the same. So that's 4, 12, and 20, and then the sum of the second differences is 8. Second difference is the same, or difference of the differences is the same. Series is quadratic. Now, it's time to make it's time to make the, what's it called? Sorry, it's time to make the formula. Now it's T1, T2, T3, and T4. Okay, so we have all of them there. And what we're going to do is we're going to say that it's a quadratic series, so we're going to use the generic an squared plus bn plus c. This is not in your maths table, so please remember it's very similar to the minus b formula, the general quadratic equation. Okay. Now, what we know about the a value is it's half the second difference, so we know the a value is 4. Okay, so a value equals a half of 8, a equals 4. Now we're going to sub in. We're going to do T1 first, which is 4 times 1 squared plus b times 1 plus c, and it's equal to 0 because T1 is 0, so we're going to get b plus c equals minus 4. Next thing we're going to do then is T2. We know T2 equals 4. So we're going to get 4 times 2 squared plus b times 2 plus c, and that will equal 4. We're going to get 2b plus c equals, now this here is 16, bring it out to your side, 4 minus 16 is minus 12. Now we have our two formulas for the simultaneous equation. So you're going to do the top one, take away the bottom one, so it's going to be red one, take away black one. and I should get a b equals -8 when I do that, and that's exactly what we're expecting, b to be -8. And then when you solve the other part of this equation, so you get a -8 plus c is -4, and then you get c equals 4. Go back up and finish out your equation. Tn therefore is 4n squared minus 8n plus 4. Happy days. Alright, next question. Find an expression in n for the total number of grey squares in the n pattern, and hence find an expression for the total number of squares in the n pattern of the sequence. Okay, so I think it's going to want me to do nearly exactly the same thing as the white squares, which will be interesting. So I'll get on that now. Okay, so the grey squares, T1, T2, T3, and T4. The grey squares is 1, 5, 9, and 13. And we can see that the grey squares is in the aromatic sequence, or arithmetic sequence. Okay, so Tn equals A plus n minus 1 times D. And the A value is the first term, so Tn equals 1. The D value is 4, so it's going to be 1 plus 4n minus 4. And that's going to be 4n minus 3 for Tn. Now, if you remember correctly, the total, what's the total squares, is it? Total number of squares. So total squares equals grey squares plus white squares, okay? And we already know what the we know that the grey squares is 4n minus 3, and we know that the white squares is 4n squared plus 8n, sorry, minus 8n, 4n squared minus 8n plus 4. We'll add the two down together, and what we should get is 4n squared minus 4n plus 1. Now, you might not notice this, but it's actually also a perfect square. Now, you'd get full marks for that, but just to make you aware, just in case you didn't know, if you were to factorize that, you'd get a 2n minus 1 by 2n minus 1, which is 2n minus 1 to be squared. Alright, happy days. Now, what does it want from me next? One of the patterns in the sequence has this many squares in total. Find the number of grey squares in this pattern. No bother. So we're talking about total squares. Well, the total squares is the equation we had earlier here, which is your this equation here. So we say 4n squared minus 4n plus 1 equals 5041. 4n squared minus 4n, and then bring it over the other side, minus 5040. Now look, you can do the minus b formula. A is 4, B is minus 4, C is minus 5040. Do the minus b formula, lads. I'm hoping we all know how to do a minus b formula by now. And your two answers will be what's it, 36 and 35. So you'll get n equals minus 35. Can't be a negative number, so that's wrong. And then the other one is n equals 36, and that is the expected number. Now we're asked for the number of grey squares, so you go back to the grey square formula, which is 4n minus 3. So it's going to be 4 times 36, take away 3, and you're going to get 141 grey squares. Alright, awesome. Prove by induction that the sum of the white squares in the first n patterns is given by the following formula. Okay, give me a second with that. Okay, let's keep going. Now u1 is 0, u2 is 4, and U3 is 16. We got that from our expressions of the white tiles from earlier. Okay. Wait a minute. Alright. So here we are. Now we're going to do plus un then. So plus dot dot dot, and we know that un is this much here. 4n squared minus 8n plus 4. And that has to equal your 2n minus 1, n minus 1 over 3. Okay. We're going to prove true for n equals 1. Okay. So that would mean that u1, and remember this is essentially s1, right? Such that u1 will equal s1 such that 0 equals 2 times 1, 2 times 1 take away 1, and then it's 1 minus 1 all over 3. Now the 1 minus 1 part here, that's 0, and everything else multiplied by 0 is 0. So then we get 0 equals 0, and it's true for n equals 1. Now, assume true for n equals k. So all this I wrote earlier. So I'm just going to steal it, okay, from earlier. And here's what we're going to do with this. Anywhere I see an n, it's going to become a k. So that's k, 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 and k. So assume true for n equals k. Now, next one. Test or prove true for n equals k plus 1, or test. So here's what we're going to do. So this is going to be exactly the same stuff here. So I'm just going to clone all this. So Control D. Oops. Must have missed the other part there. Plus dot 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 plus 4k squared minus 8k plus 4. Now please remember that u1, u2, u3, and this is un, and this was sn, okay? But it wants k plus 1, so I have to do u of n plus 1 as well, okay? So u of n plus 1, I'm going to reduce this size because it gets quite large, this equation, okay? So I have to put in u of n plus 1, which means anywhere I see k, or u of k plus 1, anywhere I see k, I have to put in k plus 1 because that's uk. Now I have to do uk plus 1 because there's an extra term added on. So it's going to be 4 times k plus 1 squared minus 8 times k plus 1 plus 4. Now, instead of doing s of k, we're doing s of k plus 1. So anywhere I see a k, I'm going to put in k plus 1. So it's 2 times k plus 1, and that's 2k minus 1 there. I just need a bit of extra board to work with here. So I'm going to do 2k, so it's going to be 2k plus 1 take away 1, which is 2k plus 2 take away 1, which is 2k plus 1. And the last part is k minus 1, so it's going to be k plus 1 minus 1, which is simply k. And that's all over 3. Now, what we assumed in the last question in part 2, we assumed that all of this was the same as sk. So all this part is sk, and sk is this formula here. So we can replace the yellow part with this Okay, and then I'm gonna to be honest, this looks very messy. Okay, and that's going to be plus. Now I'm going to probably multiply this out where that's k squared plus 2k plus 1 multiplied by 4, 4k squared plus 8k plus 4, and then minus 8k minus 8 plus 4. I'm going to fix all that up now. The 8k's cancel, and the numbers actually cancel as well, so it's just 4k squared, okay, which is handy. So all that just turns into 4k squared, which is really handy. Now I'm going to give a common denominator of 3, so instead of using 4k squared, I'm going to use 12k squared over 3, and now I have to prove that it equals this on the right hand side. Now you could multiply both of them out and just prove they're the same that way. It might not be the worst move for this type of question. It's a bit of a pain, alright, but it would be probably the safer bet. Yeah, let's multiply it out and see if they're both the same. Alright, so I'm going to multiply this out. That's 4k squared minus 2k, and now I'm going to multiply that by this here as well. Okay, so we get 4k cubed minus 4k squared minus 2k squared plus 2k, and then plus your 12k squared. Now they all have a common denominator of 3, so I can deal with that. And then this is going to become 4k cubed minus 6k squared plus 12k squared. So minus 6k squared plus 12k squared is plus 6k squared plus 2k all over 3. Now I wonder if we could turn it back into this. Just multiply it out. So that'd be 2k plus 2. Oh, actually let's make this faster. See that k at the back? I'll move it to the front. Then multiply 2k by k, and I get 2k squared plus 2k. And then I'm going to multiply that by 2k plus 1. So we get 2k squared by 2k, which is 4k cubed. And then 2k squared by 1 is 2k squared. And then 2k by 2k is 4k squared. And finally 2k by 1 is 2k. And that's 6k squared as well, plus 2k. So true for true for n equals k plus 1 if n equals k is true. Hence by the principle of mathematical induction, it's true for all n element n. Remember, n has to be a natural number. It's u1, u2, u3, or t1, t2, t3. There's no negative numbers or fractions or whatever. Alright, this is quite the question. It's very long. C2. Hence or otherwise find an expression in n for the total number of squares for the first n patterns in the sequence. Give your answer in its simplest form. Alright, and you're almost in disbelief that this question is still going on and you're not done yet. Okay, I'll have a think. Once again, total number of squares is your grey plus your white, okay? And it's the sum of the series, so it's the Sn for the grey series and the Sn for the white series. And we have the Sn for the white series. The Sn for the white series is this formula here from earlier. Oh, sorry, yeah, it's actually in the question. It's this formula here. Alright, so it's 2n bracket 2n minus 1 bracket n minus 1. So 2n minus 1, n minus 1 all over 3. Now, we have to get the sum of the series for the grey one, alright? Now, it's an arithmetic sequence, okay? The grey one was. So, you look up your sum of a series for an arithmetic or arithmetic sequence, and this is what you get. And what did we learn about the grey sequence earlier? The grey pattern was T1 was 1, T2 was 5, T3 was 9, and T4 was 13. So it's a D value of 4 and an A value of 1. So we create this here. So 2 times 1 is 2. That's 4. So that'd be 4n minus 4. And then we get n over 2. N over 2 into, what's it, 4n minus 2. Now divide it by 2. And we get 2n minus 1 times n. So it could also be written as 2n squared minus n if you want, right? So we worked out all that, and I'm going to go for n into 2n minus 1. Okay, so I'm going to get rid of all this. Now you're wondering, why did I choose the second one? Well, if you look really closely, n into 2n minus 1. See the way they have this as a common factor? See the way that's a common factor of both of them? Now, if I just put them over 3, you're a 3 and you're a 3. Okay? So now we have something in common. Okay? Now what can we take out that they have in common? Well, we can take out the 2n minus 1 and the 3 from both of them. And what we have left over is 3n, and then we have a 2n multiplied by n minus 1. Now I'm going to explore that by multiplying it out. I'm going to get 2n squared minus 2n. And then if I add on the 3n, it's going to be 2n squared plus n. So I'll just rub all that out and just write down 2n squared plus n. And then I can factorize out n as well. So factorize out n, and that's basically n into 2n plus 1 when I factorize that part out. And n into 2n plus 1. And I believe that's actually my answer. I can just leave it like that if I want. The solutions multiplies it out into 4n cubed minus n over 3 when you multiply it all out, but I don't see the need to do that either, so it's whatever way you want to present the answer at the end of the day. Alright. Oh god. Still not over. There are 97 grey squares, alright? There are 97 grey squares in the n part of the sequence. Find the total number of squares in the first n patterns of the sequence. Oh god. Okay. So we're talking specifically about the grey pattern, okay? So if we're talking specifically about the grey pattern, Tn for grey is 4n minus 3. And you're talking that equals 97. then for n must equal 100, and this means that n is 25. It's the 25th pattern that has 97 grey squares. Now find the total number of squares in the first n patterns of the sequence. Well, that means we got to go to the formula we made a second ago, which is basically this formula here. Okay, so I can use this formula right here. Okay, so I'm actually just gonna copy and paste it, because we discovered that in the last question, that is the total amount of squares in the full thing. Okay, and here you go. Now, anywhere C n, I'm going to replace with 25. So 2 times 25 is 50. 50 take away 1 is 49. It's 49 over 3. N itself is 25. 2 times n is 50. 50 plus 1 is 51. You're going to multiply this out, and you should get 20,825. We'll obviously check that out. 49 over 3 multiply by 25 multiply by 51. There you go, 20,825 as predicted. Alright, I'm going to save this one because I'd be ashamed if I lost it.